Good morning. Now let's start our new topic, which is nonlinear regression models. Till now, we are talking only about linear regression models. In this course, or even in the regression course taken before, we were talking about linear regression models. And of course, as you all know, by linear, we mean it is linear in the parameters. Our main concern is in the parameters. So if the regression model is linear in the parameters and variable, it's called linear. While if it is linear in the parameters but non-linear in the variables, still it's called linear. Why? Because our main concern is in the parameters. A linear regression model is a linear in the parameters. For nonlinear regression models, we have to differentiate between two concepts, which are intrinsically linear and intrinsically non-linear regression models. So starting with the intrinsically linear model is still a nonlinear regression model. But using a suitable transformation, it can be transformed from nonlinear to linear. So the intrinsically linear model is nonlinear, but can be transformed to be linear. We can use any transformation or a suitable transformation to transfer it from nonlinear to linear. But the intrinsically nonlinear regression model, again, it is nonlinear, and there is no transformation that can be used to transfer it from nonlinear to linear. I cannot transform it from nonlinear to linear. It cannot be transformed. There is no transformation to transform it from nonlinear to linear. So intrinsically linear and intrinsically nonlinear, both are nonlinear regression, but the intrinsically linear can be transformed while the intrinsically nonlinear cannot be transformed. So of course, our main concern will be in the intrinsically nonlinear regression model. And for simplicity, we will call it directly nonlinear regression model. So from now on, we mean by nonlinear regression model, a model that cannot be transformed to be linear. Now, for example, if we have the following example, now starting with the first example where y equal beta naught plus beta 1x plus u. In this example, of course, it is linear from the very beginning because beta naught and beta 1 are linear. In the second example, y equal ln beta naught e to the power beta 1x plus u. Maybe from the very beginning you will say that it is nonlinear, but actually if we let beta naught star equal ln beta naught, so this is beta naught star, and e to the power beta 1 equal beta 1 star, so this is beta 1 star. So I will have a model which is y equal beta naught star plus beta 1 star x plus u, which is linear. What about the third example? It's very clear that it is nonlinear completely. Why? Because beta naught and beta 1 are nonlinear. But after taking the ln transformation, now we have ln y equal the power, which is beta naught plus beta 1x plus u, multiplied by ln e, and of course we know that ln e equal 1, so ln y equal beta naught plus beta 1x plus u, and this is a linear regression model with a transformed predictive values or a variable, a dependent variable y. Instead of y, we will have y star, for example, which is ln y. For example number 4, we have y equal beta naught x1 beta 1 x2 power beta 2 u. Again, of course, it's very nonlinear. Why? Because we have beta 1 and beta 2 not linear. And in this case, this model can be transformed to linear as well. How? If we take the ln transformation, so again it will be ln y, ln beta naught plus the power beta 1 multiplied by ln x1, the power beta 2 multiplied by ln x2, as if I'm having a new regression model, which is y star equal beta naught star plus beta 1 x1 star plus beta 2 x2 star plus the new error term, as if I am making certain transformations to the variable to transform it from nonlinear to linear. So this model is called intrinsically linear model. And 3 and 4 are called intrinsically linear model. Why? Because using the transformation, I can transform it from nonlinear to linear. So it is intrinsically linear. What about number 5? Number 5 again is nonlinear, but is there any transformation that can transform it from nonlinear to linear? Can you transform this model from nonlinear to linear? Actually, there is no transformation that can be used. So this model cannot be transformed from nonlinear to linear. So this model is intrinsically nonlinear regression model. And for simplicity, as we said, we will call it nonlinear regression model. It's a nonlinear regression model and we cannot transform it to be linear. So now how to make estimation or fitting for the linear and nonlinear regression model. We have two models, model 1 and model 2. This is model 1. And this is model 2. Model 1, of course, is very clear. It's the linear regression model. So how to estimate model 1? How to fit model 1? It's very simple, using the OLS, the ordinary least square. We will apply the ordinary least square by minimizing the squared residuals, the sum of squared residuals. Summation ui hat squared. You have to minimize summation ui hat squared. Differentiate with respect to beta naught and beta 1, equate to 0, and find beta naught hat and beta 1 hat. I think you are familiar and know this procedure very well from the previous course of regression. What about model number 2? Model number 2, y equal beta naught e to the power beta 1x plus u. Again, this is nonlinear and it cannot be transformed to be linear. I cannot transform it to be linear. So it is nonlinear regression model. And actually this model is called exponential regression model. It's very important and it's very common in economics. Actually, it can be used to study population, GDP, or money supply. It's very important model, this exponential regression model. So how to fit this nonlinear regression model or any nonlinear regression model? Now again, if we apply the same procedure of the OLS, which is minimizing the residual sum of squared, obtain the residual sum of squared, y minus y hat, and square it, and then minimize the sum by differentiating with respect to beta naught first, and then differentiating with respect to beta 1 first, in order to obtain the what's called the normal equation by the same procedure of the OLS. But in this case, you will end up with the following normal equations given here. These are the resulting normal equation from minimizing the residual sum of squared of model 2. I will differentiate with respect to beta naught and equate to 0. And then I will differentiate with respect to beta 1 and equate to 0. At the end, I will have these two normal equations. And of course, these two normal equations cannot be solved simultaneously. I cannot find an explicit solution for beta naught hat and beta 1 hat. You can try it by yourself. Please try to find these two normal equations by differentiating with respect to beta naught and beta 1 and equate to 0. You will end up by these two equations, and these two equations are highly complicated and cannot be solved simultaneously. You cannot solve these two equations. In other words, you cannot find the value of beta 1 hat and beta naught hat. You cannot find the explicit form of beta naught hat and beta 1 hat. You cannot say that, or you cannot find the formula like in the linear regression saying that beta naught hat equals y bar minus beta 1 hat x bar, or beta 1 hat equal summation deviation xy over summation x squared. We cannot find these explicit forms. You cannot find solution for these two equations. Unlike the normal equation in the case of linear regression model, the normal equation for nonlinear regression model have unknown in both the left and the right hand side. We have beta naught hat and beta 1 hat in the two equations in the left hand side and in the right hand side. So we cannot obtain an explicit solution for these unknowns. We cannot solve it. The unknowns are expressed in terms of themselves and the data itself. So we cannot use the OLS, the ordinary least squared, in order to estimate or in order to fit non-linear regression model. Why? Because the two normal equations will be highly complex and we will not be able to find the explicit form of beta naught hat and beta 1 hat like in the case of the linear regression model. So what should we do in this case? The first method that can be used for estimating nonlinear regression models is called the trial and error method. And actually it consists of 3 steps. In step number 1, all what you need to do is just set initial values, set values, assume values, guessing values. You are guessing values for the parameters. So if I have beta naught and beta 1, I am guessing values for beta naught hat and beta 1 hat. Just guessing either by a previous experience from previous work or just guessing, or you can fit a linear regression model and obtain beta naught hat and beta 1 hat and use them as initial or guessing for the values. And then in step number 2, you have to use these guessed values or these initial values to fit the model and find the error sum of squared, the residual sum of squared. So I am assuming a certain values for beta naught hat and beta 1 hat. For example, assuming values, so let beta naught hat equals 0.1 and beta 1 hat equals 0.2 or 0.3 and 0.05, any two values for beta naught hat and beta 1 hat. And then use these values to find the residuals, the squared sum of residuals. And then in step number 3, try another values for beta naught hat and beta 1 hat. So in the first step, you have tried 0.1 and 0.2, try 0.3 and 0.4, 0.6 and 0.5, any two values for beta naught hat and beta 1 hat. And then again, find the residual sum of squared. And then compare between these residual sum of squared. And of course, you know that we are searching for the least residual sum of squared. So simply you will pick the values that give you the least sum of residuals, the squared residuals. So it is simply numerical. That's why it's called trial and error. You are trying different values of the parameters, different values for beta naught hat and beta 1 hat. So we are trying values and find the corresponding residual sum of squared. And finally, compare between these residual sum of squared in order to pick the one that give you the least residual sum of squared. Of course, there are problems with the trial and error method. First of all, how do you know that you have reached the lowest possible error sum of squares? You have to try all possible combinations of the two parameters, which is infinite number. You cannot reach all possible combinations of the values. So how do you know that you have reached the lowest? You may try 100 values, 1,000 values, 2,000 values, but still the 2001 will give you the lowest, will give you the best solution. So there is no guarantee that these values will give you the lowest value or the best value. And of course, it's very time consuming. The trial and error process may ultimately produce values of beta naught and beta 1 that may guarantee the lowest possible error of some square, but you cannot, and it's very time consuming. It takes a lot of time and it takes a lot of effort to find a lot of calculations. So first of all, it's time consuming, and second, there is no guarantee that the solution that you have reached is the best one. So we can try another method. The second method that can be used is called the direct optimization, and actually we are not going into the details of this method. It includes some iterative routine called for solving the normal equations resulted from differentiating the sum of squared residuals. As we said, the main problem was in the normal equations, so there are some numerical methods that can be used. There are some optimization methods that can be used with these normal equations, for solving these normal equations. And one routine is called the method of steepest descent, but as we said, we are not going into the details. The last method is the iterative linearization method, and this is the most important one. It consists of 3 steps. In the first step, we are linearizing a nonlinear equation. We are trying to linearize equation. As we said, it is used with nonlinear regression equation. So we are trying to linearize this nonlinear equation around some initial values. And again, these initial values, how can we obtain these initial values? As we said, by guessing, by previous work, by experience, or you can just fit a linear regression model and use the estimated values as initial values. So first of all, linearize around some initial values. And then in step 2, since we are now having a linear regression model, so we can simply apply the OLS. Since it is linear, we can apply the OLS and obtain the fitted values or the estimated coefficients. And then in step number 3, we are relinearizing. We are using these fitted values or these estimated coefficients to relinearize the model in step number 1, as if we are back to step number 1. That's why it's called iterative linearization method. Why? It consists of iterative. It is like a loop. It's like an algorithm. We are start by linearizing using some initial values, as will be seen later how to do this. But we are starting by linearizing around some initial values. And then we fit the linearized model by the OLS and obtain the estimated coefficients. Then use these estimated coefficients to relinearize 1, 2, 3 again, and then back to 1, 2, 3, and then back to 1, and so on. That's why it's an iterative process. It's an iterative process. It consists of iterative. It's like as we said, like a loop or an algorithm. But when this process stop, when to stop? Actually, this process continue until what is called convergence. And by convergence, we mean that there is no substantial change in the estimated values from the last couple of iterations. As if I have 1,000 iteration. So in the 1,999 iteration, the last couple of iterations, the difference between the last couple of iterations can be ignored, approximately equal to 0. There is no substantial change in the estimated values from the last couple of iterations. The last couple of iterations gave me approximately equal values. The difference between them are approximately equal to 0. That's the meaning of convergence. So this process is continued until convergence. Or sometimes you can specify the number of iterations. You can say that I want this process to end after 100 iterations, 1,000 iterations, 2,000 iterations, whatever the number of iterations is. But the most common way and the best way is leave it until convergence, until there is no substantial change in the estimated values of the last couple of iterations. Now, how to do this? As we said in the first step, we are linearizing. We are linearizing the nonlinear equation around some initial values. How to do this? Of course, all of you are familiar with the Taylor expansion. The Taylor expansion takes the following formula. This is the formula or the form of the Taylor expansion. And the Taylor expansion can be used to put any equation in any polynomial degree. So you can transform any equation into any polynomial degree around some initial values. And if I want to linearize, if I put it in the first degree, so I will take only these 3 terms. and these extra terms will be used if I want to put it in a second order, and so on. So the Taylor expansion will be used to linearize the nonlinear equation by using these terms, and we are assuming initial values. So in this case I have function f of x and y, and f of x and y are nonlinear. I'm going to assume some initial values a and b. Using these values a and b, I can put f of x and y into a linear regression, or a linear equation using these a and b initial values. So what is FAB? FAB is the function needed to be linearized, but after substituting with a and b. So if a equals 0.1 and b equals 0.2, you can just substitute in your function by 0.1 and 0.2. These are the initial values. Remember that we said we are linearizing around some initial values. These are the initial values, the assumed values from the very beginning. So substitute in your function by these two values. And then x minus a again is the value, the assumed value. What is fxab? If xab is the partial derivative of the function with respect to x. So I will differentiate my function f of xy with respect to x only, and then I'm going to substitute by a and b again. And by the same way, what is fyab? Fyab again is the partial derivative of fxy with respect to y in this time, but substituting with a and b. So these two terms are obtained by differentiating with respect to x and substituting with the initial values, and differentiating with respect to y and substituting with the initial values. So using the Taylor expansion and some assumed values, some initial values, we can put the nonlinear function into a linear one. How? First of all, the first term substitute by the initial value. The second term, differentiate with respect to x and substitute with the initial value. The third term, differentiate with respect to y and substitute by the initial value. This is the definition of the Taylor expansion. This is the definition of the Taylor expansion. And we will see later how to use this definition in order to linearize any regression equation. Finally, estimating nonlinear regression model using Taylor series expansion is called the Gauss-Newton iterative method or the Newton-Raphson iterative method. Actually, these algorithms are very common in statistics. The Gauss-Newton iterative methods and the Newton-Raphson iterative methods are very common, and both of them are based on this Taylor expansion. They are based on linearizing the function around initial values and then relinearize until convergence. Now, we want to apply this procedure into our regression model. Now I know the basic idea, which is I need to linearize around initial values, and then it is linearized. I will fit it and find the estimated coefficient, use it to relinearize again. But how to do it in regression equation? So back to our example, again, assume we have the following regression equation, which is y equal beta naught plus e beta 1x plus u. And again, as we said, this is nonlinear and cannot be transformed to linear. It's intrinsically nonlinear. So how to apply the Newton-Raphson method or the iterative method for fitting this nonlinear equation? And again, let me remind you again with the Taylor expansion. This is the Taylor expansion, the formula of the Taylor expansion used to linearize the function around some initial values. Now, in this case, this is the nonlinear function. Beta naught e beta 1x is our f of beta naught and beta 1. This is the function needed to be linearized. This is the nonlinear function needed to be linearized. So this is as if instead of x I'm having beta naught, and instead of y I'm having beta 1. So f of beta naught beta 1 is my f of xy in the Taylor expansion. Again, my equation needed to be linearized is beta naught e to the power beta 1 x, as if this is f beta naught beta 1, as if instead of x in the Taylor expansion I'm having beta naught, and instead of y I'm having beta 1. So I'm going to apply the iterative method. Step number 1, we are going to assume some initial values. Assume some initial values for the parameter. Say it will be beta naught star and beta 1 star. Beta naught star 0.1, 0.2, 0.5, 0.6, 3.8, 5.4, any two values, any initial values, any two values. Again, I'm reminding you how to find these initial values. Previous experience, work, you are just guessing, anything. So step number 2, we are going to linearize around these initial values beta naught star and beta 1 star using the Taylor expansion. So as we said, instead of x, f, x, y, we have f beta naught beta 1. Instead of a, b, we have the initial values beta naught star, beta 1 star. And instead of x, we have beta naught. Instead of a, we have beta naught star. Instead of fx a b, x is beta naught, as if I will differentiate this equation with respect to beta naught, and then I'm going to substitute with beta naught star and beta 1 star, plus beta 1 minus beta 1 star. F, instead of fy, we have f of beta 1, f of beta 1, beta naught star, beta 1 star, as if I am differentiating this equation with respect to beta 1, and then I will substitute by beta naught star, beta 1 star. So now, step number 1, we have assumed some initial values for beta naught and beta 1. Let this be beta naught star and beta 1 star. And then we are going to linearize using the Taylor expansion, using this formula. But instead of x and y, we have beta naught and beta 1. And instead of a and b, we have beta naught star and beta 1 star. Now, we have to differentiate with respect to beta naught and substitute with beta naught star and beta 1 star, which is given by this formula. F of beta naught star, beta 1 star. Differentiate this equation with respect to beta naught. If I have differentiated this equation with respect to beta naught, it's simply equal e to the beta 1 x. And then substitute by the initial value, so it is e to the power beta 1 star x. And again, f of beta 1, beta naught star, beta 1 star, as if I am differentiating, but in this time I am differentiating with respect to beta 1. So if I have differentiated this equation with respect to beta 1, it is beta naught e to the power beta 1 x multiplied by x, and then substitute by beta naught star and beta 1 star. So now f of beta naught beta 1 equal f of beta naught star beta 1 star. And what is f of beta naught star beta 1 star? I am substituting with beta naught and beta 1 star in my equation, so it is beta naught star e to the power beta 1 star x, and then beta naught minus beta naught star, and then the differentiating with respect to beta naught and substituting by the initial values, which is e to the power beta 1 star x, plus beta 1 minus beta 1 star beta naught star e to the power beta 1 star x multiplied by x. So now this equation beta naught e to the power beta 1 x are now linearized. Why? Because beta 1 and beta naught are linear now. Remember that beta naught star and beta 1 star are values, are assumed values, equal 0.1 or 0.2. They are constant values, they are values. But the parameters itself, beta naught and beta 1 in f of beta naught and beta 1 are now linear. It is linear. It's a linear function. We can just make some simplification saying that y equal this f of beta naught beta 1 plus the error term, substituting this function by and plus the error term, and then y minus beta naught star e to the power beta 1 star, and let beta naught minus beta naught star equal alpha 1, and e beta 1 star x equal x1 star, and let beta 1 minus beta 1 star equal alpha 2, and this quantity is simply call it x2 star. So I will end up with a linear regression model but with new transformed variables. Instead of y, I have y star. Instead of x, I have x1 star. Instead of x2, I have x2 star. Instead of beta 1 and beta naught, I have alpha 1 and alpha 2. Now, this model is a linear model. It can be simply fitted using the OLS. So, we will simply apply the OLS. We will apply the OLS in order to fit this model. And we will obtain alpha 1 hat and alpha 2 hat. From alpha 1 hat and alpha 2 hat, we will obtain the values of beta naught and beta 1. How? We said beta naught minus beta naught star equal alpha 1. So simply beta naught equal alpha 1 plus beta naught star. And we said beta 1 minus beta 1 star equal alpha 2. So simply beta 1 equal alpha 2 plus beta 1 star. So we will fit this model using the OLS, and then we will obtain the new values of the coefficients beta 1 and beta naught by using alpha 1 and alpha 2. So now I have new values. Instead of beta naught star and beta 1 star, I have beta naught double star and beta naught double star and beta 1 double star. Then I will use these values to relinearize using the Taylor expansion. So I will repeat the same steps starting from step 1, but instead of having beta naught star and beta 1 star, I have beta naught double star and beta 1 double star, and then 2 and 3, and then you will have beta naught 3 stars, beta 1 3 stars. Use it to relinearize. Beta 4 stars, use it to relinearize, and so on and so on and so on until convergence. And again, what do we mean by convergence? We mean that the last couple of iterations, the last betas, say beta 99 stars and beta 100 stars, are very close to each other. The difference between these two values, the last two values, are very close. The difference between the last two values are approximately 0. There is no substantial change in the estimated coefficients. Again, this is an iterative algorithm. It starts by an initial values, and then we linearize using the Taylor expansion to obtain a linear equation, find it using the OLS, and find the new estimated values, and then relinearize again, and so on until convergence. Now there are some remarks concerning this method, or the iterative linearization method. First of all, concerning the normality, even if the error terms are normally distributed, the nonlinear least square estimate are not normally distributed. So even if the data are normal, the estimates are not normal, because as we said, it's not obtained using an explicit form that can be shown to follow normal. It is obtained numerically, and they are not unbiased and do not have minimum variance in small samples. As a result, we cannot use the usual t-test or the f-test. While for large samples, means asymptotically, the nonlinear least square estimates are approximately normally distributed and almost unbiased and have almost minimum variance, asymptotic optimal properties. So in small samples we cannot apply the usual t-test or the f-test, but in large samples asymptotically it follows normal, so we can apply it. Then summation u hat is not necessarily equal to 0. Summation the residual does not necessarily equal 0, and therefore from this remark, therefore SSR plus SSE is not necessarily equal SST. So since summation the residual may not equal 0. So summation the explained sum of squared and the residual sum of squared may not equal to the total sum of squared. So from this remark, can we use the r squared or the adjusted r squared? Of course not, because the r squared or the adjusted r squared is based on the idea that the residual sum of squared and the explained sum of squared added up to the total sum of squared. And if this is not satisfied, we cannot apply the r squared nor the residual, the adjusted r squared. And finally, the rate of change of y with respect to x is dy over dx. It is not beta. It is not beta. It is dy over dx. And it can be obtained for each equation separately. For each equation, you have to differentiate the equation with respect to x in order to find the rate of change of y with respect to x. It depends on the form. It depends on the functional form itself. For each one, you have to obtain the derivative with respect to x in order to find the rate of change. Actually, we finished this topic, which is nonlinear regression model. To sum up, as we said, we have to know what is the meaning of nonlinear regression model, what is the difference between intrinsically linear and intrinsically nonlinear, how to fit intrinsically nonlinear model, what are the possible ways that can be used, and the most important one is the iterative linearization method, how to apply it using any given formula, any given nonlinear equation. And finally, what are the remarks, what are the notes that should be taken into consideration concerning this iterative method. Thank you so much.